Welcome to the lecture for week 2. Today we're going to focus on population growth, and we're going to use stock and flow systems as a cognitive tool to help us understand population growth. So the themes for today are everything is connected. You can come back later and click on this link in the slides just to see a little diagram, but the point is that all aspects of human society, economy, and the environment are connected. So when we try to talk about how human population growth is controlled, we're really talking about a heavily interconnected system, not a simple cause and effect from a few factors. As we mentioned before, population size may drive the environmental impact. It's one of the parts of the IPAT relationship. And we're going to develop this idea that the growth rate of human populations varies depending on many factors, including sort of the wealth of the society, education, and women's rights, especially as these pertain to choices that individuals and families might make. And we're going to use stock and flow systems to help us understand this problem, sort of like in last week how we used the IPAT relationship to dig into problems, and we used problem types as a way to try to identify what the key aspects of problems were. So in this presentation today, we're going to review the IPAT relationship, and I'm going to talk a little bit about how we use that by reviewing the answers from the week 1 crux question. I'm going to present some growth models for animals and plants that are applicable. We'll talk about what a model is and how we use these different types of models. And the point there is that human population growth models are very different than animal population growth models. Then we're going to learn this systems approach, this stock and flow systems. We'll look at the approach, we'll apply it to human population growth, and then use that as a basis to start talking about the demographic transition. And finally, we're going to use that same stock and flow systems approach to look at the environment and health interaction we saw before, and specifically the impact of malaria. So let's just quickly review the IPAT relationship, which is just impact is related to the population, affluence, and technology. Now I want to go to this is a way to look at problems by figuring out how the impact is related to these different factors and how these different factors interconnect. So let's look at the crux question 2, when I wanted you to respond to how the IPAT relationship could be applied to either diapers or milk. And when I said don't give me the kill the children response, it's if you want to reduce impact, you could reduce the number of people on the planet and generally kill everybody. And that's really sort of the plot in Dan Brown's Inferno. So that's a great book, but it's not something we're considering here. So the point of the IPAT relationship for this course is by identifying what's the population, what's the influence, what are technology approaches that could be considered, makes you look at the problem and sort of take out the pieces and then try to put them together. So in particular, the idea about what population uses diapers. A lot of you assume that it was just children because you'd just been watching those videos, but there's a growing population of Americans, in particular of adults, older adults, that are using diapers as part of their daily regime. So that just analyzing what's the population is important. How does consumption relate to that? What are the choices in consumption? You might have a whole range of choices that you should consider, and that also relates to the technology for composting or cleaning or creating new types of diapers. So just a few points. You can read these comments for yourself later, but the point about the technology is not only what technology we might use, but if we don't use one, what are the alternatives? And this is something we always want to consider. So when we say technology, we're really talking about what's the range of alternatives. So you should look over these responses to week 1 crux question, and also look at the examples for week 2 crux question before you launch into that again. Okay, now when we are talking about population growth, we're going to be considering several different models, and I want to just go through some definitions here. So a theory is when there's considerable evidence. A lot of scientific work has gone into this, and this is not how theory is used in colloquial English. And a hypothesis is something where we have identified a question that can be answered and set it up so that it can be proved or disproven, and that's really a hypothesis. But we're going to talk about models today, and these are representations of the real system, and they're simplified, many times, especially in our case, oversimplified. But the reason models aren't hypotheses is that they're not set up to be disproven, they're set up to illustrate some behaviors of the real world system. And there's a lot of types of models that might use in science, and some are simple, and we use those to gain insight. That's the type we're going to be using here. Really highly simplified models that give us insight into the problem. But we could also have some others that were busier or used to fit particular set of data. Those might be more mathematical or statistical type models. We're not going to really talk about those much in this class. So the growth model that we're going to be interested in is this exponential growth model, and that's just one of the alternatives to many different types of models. And we're going to see that that is part of the that exponential growth is part of a population model that we're going to apply to look at humans. But looking at these population growth models, I explain this in more detail in the little video called the Excel simulation, about how with a constant rate of increase, where you just have the same growth rate per unit time per population, after time the curve will get steeper and steeper, and that's because of sort of the compounding. The beginning of the growth curve, there's very low population, and so therefore the growth rate times the population as a net increase is a smaller number. You get up with higher populations, that same growth rate times a larger population gives you a bigger increment. You should look at the explanation I have for that in the Excel simulation. Another type of model that we look at is just basically a resource limitation model. And one particular formulation of this is called the logistic equation. That is a simple mathematical formula that describes this blue curve. This blue curve has rapid growth when there's lots of resources, and then the growth slows down when the resources are limited. And in the logistic growth equation, that one mathematical formulation, like I said, R controls the initial rapid exponential-like growth, and K controls the level, the final level that the population can go to. This equation does not apply to human populations, and to try to talk about the carrying capacity, this K number up here, this carrying capacity, as something that's can be described with a biological model is really sort of out of whack. Human populations controlled by social and economic forces, not by resource limitation. So to set a carrying capacity, or even call it a carrying capacity, is sort of a misuse of this logistic equation. You see it all the time. I'm just warning you that that's sort of something to be wary about. Now there's three other types of models that are related to that same formulation of resource limitation controlling growth rate. And again, like I said, those don't particularly pertain to human population growth at the level of countries. And that is, one is oscillation, where when the population exceeds the carrying capacity, after that you have a negative growth rate and it drops below, comes back up, drops below, comes back up. This oscillation around the carrying capacity can happen in animal populations. It's been observed. And damped oscillation, like the one shown here, sort of homes in on the carrying capacity. very similar setup can happen when you have boom and bust, which is you have this exponential growth, the resources are depleted and they can't respond fast enough. That is, the resources for the consumer, and the whole population just crashes. This is an example from Pribilof Island, where reindeer were introduced to the island and they ate up all the forage. Once they ran out, there was a bunch of starving reindeer that got sick and died. So the crash wasn't the crash was because the resources were depleted and just couldn't recover in time. And a similar one is this predator-prey, where in this case the lynx eats the hare. If there's a lot of hares around, the lynx population will grow, and then when the lynx population gets high, it depletes the hare food source, and then that cycle just starts all over again. So this oscillation is very interesting behavior in biological food webs, but again, doesn't really apply to human populations. So let's go back and look at what does apply to human populations, and that we're going to do that by taking a systems stock and flow approach. And again, this approach is similar to the cognitive tool. We're going to use a stock and flow model as a cognitive tool. Let me explain what I mean by that by illustrating the answers again from Crux assignment number 1. In that case, the question was about use the problem types as a tool to sort out the difference between a wicked problem and an information problem as it pertains to the poverty trap. And the point was to analyze the poverty trap from using both sets of tools, both sets of problem types. In one case it's just information, in one case it's information and values. So a good answer to this would be first define what a environment and poverty trap is, and then say what would happen if you looked at it as an information problem, then say what would happen as you looked at it as a wicked problem, then what's the difference. So you'll see more examples of that in the example Crux questions. So in this case, looking for the dimensions of the problem type forced you to address different components, forced you to what's the information that's needed, what are the values that are needed. So this is using that cognitive tool to open up information about a particular issue. We're going to be doing the same thing here with systems. We want to analyze the problem, and we're going to break it down into sub-processes or components, and then we're going to see how these work together. And the 4 basic things we're going to look at are stocks, which are reservoirs of some quantifiable stuff, sinks, which are sinks or sources. It's the same thing. It's either an output or an input with unlimited amounts, or it's outside the boundary of the model we're making. The flows, which can only go between sinks or stocks, and the controls over the flows. And to do this, we're going to use those 4 terms, but we're also going to use an iconography that represents those, so we can draw little diagrams. And here is a diagram, a very simple one, that has all 4 characteristics. It has a tub of water that has water in it, and that water flows to the drain. The drain is a sink. Then there's a control over the flow, and that control over the flow is just the height of the water in the tub. So very simple. And what we have is a stock is just a box. The source or sink is a little cloud. The flow is a pipe with a valve on it. And the information link is just a red line that goes from a stock to a flow, or from a flow to a flow. And we have one other little icon we might use and see here, and it's just a way to explain some of the things that are in the model. Instead of hiding all the controls of the flow in just one flow, we might use a little converter or box, or a little circle that is either constants or converters, just to sort of illuminate the model. Now, to get started, what we want to do is set the boundaries of the system we're looking at. And here's 2 different examples. If we were just going to look at deer and how much food, what happens, how much deer there are, we might be counting the deer, and then where the food comes and the flow in would be out of the system, where the feces are excreted, that's out of the system. We're only looking at the deer. But we might want to study a system where we look at the grass and the grass going to the deer, and the deer creating feces, and then that going out in the loss. And in that case, the grass and the feces would be in the system, but where the material to cause the grass to grow and what happens with the soil, those would be out of the system. So it's just arbitrary, but it depends on what you're trying to study. And the other thing we really need to do is establish what material or energy you'll be following. So in this case, we have following water from some sort of input into a tub and then flowing out. We could also study carbon or energy or water, nitrogen, phosphorus, dollars. We could study any of these, but in any particular flow and stocks, we can only study one quantity. The flow has to match whatever's in the reservoir. Can't have dollars flowing into water, can't have nitrogen flowing into phosphorus. It always has to match. Okay, let's apply this modeling approach to the demographic transition. And the demographic transition is the change in growth rate as the demographics of the population change. And we talked about resource limitation models, and these are unrealistic for people because, first, there's no such thing as a carrying capacity, and second, humans make decisions to control their fertility. They don't just leave it up to resource limitation. So here's a population growth model, and what we're just going to study is births and deaths and then the population size in some area, number of people. We're not studying immigration and emigration. Those are very interesting, but for the purpose of this class, and actually you'll see this a lot, just studying the births and the deaths. And we have birth rates controlling the births, so it's the population size times the birth rate gives you the number of births, and the population size times the death rate gives you the number of deaths. And if these are if the birth rate's equal to the death rate, then you'll find that this population size is constant. Okay. Now, the demographic transition model talks about how societies, and the one they study sort of is Europe, but it could happen anywhere, which goes through these processes. Pre-industrial infrastructure improvements results in a mortality transition. Then humans choose to have smaller families. This results in a fertility transition, and then post-industrial. And looking on this chart of birth rate, death rate, pre-industrial have high birth rate and high death rate. So the population near steady state, with both of these being about equal. Then you go into the mortality transition, where improvements in infrastructure such as healthcare, sanitation, and water supply end up decreasing the death rate. What you end up then is a net increase in population because of the birth rate is greater than the death rate. So the population grows. Then as the economy continues to increase, and in general it's a wealthier, more industrialized economy with more choices, the fertility decreases. That is, families are having smaller families. And this leads to a decrease in the birth rate. But again, during this period, there's still net growth of the population until it finally reaches post-industrial, where it's a low birth rate and a low death rate, and the population level may stabilize quite a bit. Now, the reason we're interested in this is there are many factors that relate to this. There's many factors that relate to this mortality and fertility transitions. So let's discuss that in terms of this model that we have here. We have the population in the top submodel, where births and deaths are controlling the population size. And in the bottom model, we have economic growth, and these are connected through a converter. So the wealth of the nation or of the region divided by the number of people gives you the wealth per capita. And wealth per capita seems to be a major factor in these fertility that's related to, not necessarily a cause, but related to this fertility decision. And the reason is, with more wealth, the country or the region has a lot more options available to it. And this is where all of these are related, where everything is connected. So the availability of family planning, delayed first birth, and you can read through this list to see that all of these are connected in some way. No, if you change one of them, you'll affect the other. So it's a combination of factors that lead to this change, in which humans choose to control their population, and they do that based on their perception of their own personal good and what's going to be good for their future and their family's future. And one of the things that really sets that fertility transition to have decreased birth rate is when they feel that there's a stable economy in a region that's going to provide a good life for them and their children, and without there being and they don't need a lot of children to do the big farm work or to avoid infant mortality and children mortality, so that there's at least some children there ready to take care of them when they reach old age. So all of these things work together to have the families choose to have a smaller number of children. Okay, now the problem, and we're going to address this in just a second, is what happens if you just sort of get stalled out here. You have just enough money to create nice sewers and better health care, but not enough money to really transition into a vibrant industrial or post-agrarian society. These countries get blocked here. This is called the poverty trap. They get blocked here, and there's more and more people being born, and the economy isn't growing fast enough, and that's where you end up seeing how this model can help us understand that. There's a lot of births, not so many deaths. Population is growing. As it does that, it decreases the wealth per capita unless the economic growth is just phenomenal. So that's one of the things we're very interested in, is how we can avoid this poverty trap. And a lot of these factors have to do with environment and health. Okay, now the environment and poverty, we talked about this last week, that the Millennium Development Goals had several goals in them that were related to improving the environment so that people were healthier and they led a better life. And we're going to look at that as sort of, we saw that sometimes people get in a trap where they're in a poverty zone where their current income is higher than their future income, and that's because they have to spend their current income taking care of problems right now, and they don't have any money to invest to increase their future income. Now, an example of this, I'm going to show you an example of this that relates to the environment, which is malaria. So again, this diagram here we have is the economy in using natural resources to create wealth per capita, and then down here we have human population with births and deaths, and they come together at this sort of wealth per capita. Now we can modify this model to put in sick people. So let's say we have malaria. We know malaria is let's use this just example as malaria as being this sort of sickness. We have humans, but some of them are sick and can't work, and other people are taken out of the economy of economic growth because they have to take care of sick relatives. So when you have more people that are sick, it actually costs more to run the society, but yet you have fewer people who are contributing to the growth of the economy. And then because you have less money in the local economy, you have less ability to support the facilities that are necessary to treat people, you get more sick people, and this could lead to a downward spiral. So this is an example of a trap that's caused by sickness. Now this sickness is, malaria can be very related to the environment. First of all, where people settled, they settled in sort of commerce around the world. People settled along rivers where there's a lot of water that led to more malaria. There's cultural aspects of how people deal with environmental degradation and how they treat people who have diseases. And there's industry and transportation that in a lot of areas degrades the environment by having bad roads, bad ditches, ruts in the road, bad agricultural processes lead to standing water and erosion. All of these are things that can contribute to an environment that's helps mosquitoes breed and will increase malaria impact. So the point of this is what can we do about it? What can science do about this? Well, one of the ways they can do this is by addressing where it's going to be wet and address that through climate models in time to make changes. Now we have 4 graphs here. The top 2 are when you have the highest amount of malaria, and this is the study took place in Botswana, but you can see here South Africa and Madagascar, Mozambique. These areas, this is the area of the study. And the previous model, called the CMAP, was able to predict rainfall a month ahead of time. So here's where the highest malaria was, and here's where the high rainfall was, predicted a month ahead of time. Here's where the lowest malaria was and where the low rainfall was during the lowest malaria years. These were really drought areas, and again, only with a month lead time. Well, a new set of models, which is using over 20 models put together in an ensemble of models so that they sort of can see how the models agree and disagree. And these include estimates of ocean temperature and oscillations in the longer term climate, can be much more precise about where the rain is going to fall, plus it gives about a 4-month lead time. And this 4-month lead time is critical because if you only have a month and you realize, oh man, it's going to rain here in a month, there's not a lot you can do to make changes. You can go in and spray for mosquitoes, and that's about it. But when you have 4 months, in particular if you're in the dry period before it rains and it says, oh, this is going to be a rainy time, you can get out there and smooth out some of those ruts, fix some of the sewer overflows, fix some of those things, and actually use that 4 months very, very well. And similarly, if you have 4-month lead time to say, well, it's going to be dry this year, just for malaria, you can put your money into other things for other sorts of projects instead of preparing for the rain every year just to avoid malaria. If it's going to be dry and you have 4 months notice, well, then you do other projects. So this sort of use of climate models is a good example of how an environmentally related disease like malaria can be fought more effectively with good science. Okay, now I just want to wrap up here by going back to the overview. We looked at the IPAT relationship, and I showed you how that was a cognitive tool. We looked at growth models, and I showed you the systems approach, so we could look at the demographic transition in more detail, and we used the stock and flow systems to analyze some of the components of the demographic transition, and then we extended that to look at environment and health with the particular example of malaria being an environmentally related disease and how that could be linked to science. All right, thank you.